Welcome to the Deep Dive, where we plunge into complex ideas and surface with clarity. Today, we're not just dipping our toes in, we're taking a breathtaking plunge into a truly audacious vision. Imagine if a mathematical expression, one that many of us learned as undefined 0 to the power of 00, actually held the master key to unlocking the deepest secrets of our universe. What if it unified all of mathematics and physics? It sounds wild, I know, but prepare to have your mind expanded.
It absolutely does sound audacious, doesn't it?
Yeah.
Our conventional understanding of 00 usually prompts a swift dismissal, maybe a footnote in a textbook.
Exactly.
But this isn't about a clever mathematical convention or, a slight tweak to make things fit. The paper we're exploring today presents this as nothing less than a foundational axiom.
An axiom. Wow.
One that fundamentally redefines how we perceive reality itself, its very ontology. So yes, get ready to recalibrate your understanding of numbers, physics, and maybe even the very nature of existence.
Our deep dive today is into an extensive and truly groundbreaking paper titled The Ontology of Mathematical Physics by Philip Randolph Lilien. This work introduces something called Invariant, Omnilectic Mathematics and Coherence-Based Physics. Big name.
It is. And the goal is huge, a unified ontological framework for literally everything.
For everything. Okay. Think of it then as a grand theory seeking the deepest principles, the bedrock from which structure, order, law, everything emerges.
That's right. And look, this isn't merely an abstract academic exercise. The paper confronts persistent paradoxes that have plagued various fields for decades, centuries even.
Like what specifically?
Well, we're talking about the self-referential issues that trip up set theory, like Russell's paradox.
Right.
Or even the seemingly simple question of the empty set, is it something or nothing? Really fundamental stuff. Then there's the unresolved nature of quantum measurement that still baffles physicists.
The observer effect, yeah.
Exactly. And of course, that monumental conceptual chasm between general relativity, governing the cosmos, and quantum mechanics down in the subatomic world.
They just don't talk to each other properly.
They really don't. And the core assertion of this paper, what truly drives its entire vision, is that coherence generation is the underlying source of reality. Not randomness, not entropy, but coherence.
Coherence generation.
Okay.
Our mission today, then, is to give you a comprehensive overview of this truly groundbreaking theory. We'll explore its core axiom that 00 equals 1. We'll unpack its incredibly layered architecture. Think of it as the universe's cosmic blueprint.
Cool multi-level blueprint, yeah.
And we'll touch on its vast implications across math, physics, cosmology, even AI. We've distilled the most important nuggets from this dense paper, and we're here to help you quickly grasp this ambitious and utterly fascinating vision. So let's begin our journey by asking the why. Why is such a radical proposal, one that challenges long-held mathematical conventions, even necessary? What conceptual and formal inconsistencies does this paper argue currently limit our modern understanding?
Well, historically, mathematics has been built on various foundations, right? You've got axiomatic assumptions, probabilistic interpretations, abstract structural frameworks.
The usual suspects.
Usual suspects. And they've been remarkably successful, no doubt, but they've also hit some pretty fundamental limits. They leave us with these frustrating inconsistencies, these discontinuities.
You mentioned set theory.
Yeah, take set theory. We bump into paradoxes involving self-reference, like Russell's paradox we mentioned, or even that basic, almost philosophical question about the empty set. Is it truly nothing, or is it a defined something within the system? These aren't just curiosities. They reveal conceptual, cracks, maybe, at the very bedrock of our mathematical system.
And in physics, we've got our own share of deep mysteries that feel related somehow.
Exactly. Physics grapples with the persistent quantum measurement problem.
Yeah.
How does a quantum state, this superposition of possibilities, suddenly just snap into a single definite outcome when we look at it?
The million-dollar question.
It really is.
Yeah.
And as you rightly pointed out, there's that profound, almost embarrassing disconnect between general relativity, brilliant for gravity, for the large scale, and quantum mechanics, our stunningly accurate picture of the small scale.
They just don't mesh.
They don't play nicely together at all. And the paper isn't just listing these as separate problems. It suggests they all point to something deeper, a missing foundational principle, a fundamental coherence that we haven't fully recognized.
Okay, here's where it gets really interesting. The paper introduces its audacious solution. Instead of being undefined, this framework proposes that 000 equals 1 is a foundational axiom. What does that actually mean? Not just as a number, but for our understanding of well, everything.
Well, what's truly fascinating here is that it suggests all mathematical and physical structures don't just appear based on arbitrary assumptions or probabilities.
Yeah.
They emerge from this single, profound principle.
Okay.
And this principle asserts that coherence is conserved across transformations. Let's pause on that word. Coherence.
Coherence, like harmony, consistency.
Exactly. Imagine a perfectly tuned orchestra. Every instrument, every note, aligns to create a harmonious whole. No discord, no wasted effort, just perfect alignment. This theory posits that that kind of fundamental consistency, that perfect alignment, is what drives reality, not random noise, not breakdown.
So unlike standard math or physics, where you hit these walls, undefined operations, quantum randomness, this axiom says coherence is never lost. It just gets rearranged.
Redistributed, exactly.
Yeah.
It's simply redistributed or transformed, always maintaining that fundamental harmony, that consistency. That's a truly different way of looking at the universe, isn't it?
It really is. It implies an underlying robustness.
Absolutely. And this steadfast conservation of coherence forms the bedrock of what the paper calls invariant omnilectic mathematics.
Yeah.
It's a mathematical framework where this principle is baked in from the absolute start.
This isn't just another proof within an existing mathematical system, though, is it? It feels like it's trying to define the rules of the game itself, not just win a point within it. It's almost like it's defining how mathematics becomes.
You've hit on the crucial distinction right there. The paper argues forcefully that 0, 0, 0 equals 1 isn't some trivial convention we agree on for convenience.
Right, like how we define division by zero sometimes.
Exactly. Nor is it merely a proof that fits neatly into some established mathematical box. No, it's presented as a foundational insight into the ontology of mathematics itself. What mathematics is at its most fundamental level, and crucially, how it comes into being.
Okay, so how does this transcend what we typically think of as a traditional mathematical proof? What makes it ontological?
It transcends it in a few key ways that really reshape our philosophical understanding. First, traditional proofs operate within a given system. Axioms, logic, rules they're already set.
Right.
This insight, however, is about what generates the entire mathematical system in the first place. It's like understanding the operating system before you even write an application. It's meta level. Second, it offers a truly elegant resolution to that age-old philosophical debate. Is math discovered out there in some Platonic realm?
Like finding numbers etched on cosmic stone tablets.
Kind of. Or is it invented? Just a human construct of symbols and rules, like the formalists suggest.
Like chess.
Right. This insight proposes a third way. Mathematics emerges as a process of coherence generation.
Emerges?
Yes. It's neither purely invented nor purely discovered. It's self-manifesting through these fundamental coherence principles. It grows organically, if you like.
That's a different flavor altogether.
And third, unlike traditional math that might just assume 0 or 1 as arbitrary starting points, this framework suggests that both 0 and 1 are derived from this deeper, more fundamental process of coherence generation.
So 0 and 1 aren't the bottom floor coherences.
Precisely. It completely reframes all of mathematics as an emergent structure, built on coherence, rather than one built on arbitrarily chosen axioms.
The idea that mathematics, and by extension the universe it describes, shouldn't have these jarring discontinuities, that coherence is truly fundamental, that's incredibly powerful. It feels intuitively right somehow. But how does this coherence principle actually resolve those famously undefined cases in classical algebra that have traditionally stumped us? Where does the rubber meet the road?
It's quite elegant in its approach, providing a consistent, coherent resolution instead of just a stop sign. Let's start with 0, 0, 0, 1 itself.
Okay.
Beyond the simple limit interpretation, A approaches 1 as A approaches 0, or the combinatorial argument, there's exactly one way to choose 0 things from a set of 0 things, the empty mapping.
Which always felt a bit like a trick, maybe.
It can feel that way. But the most profound justification within this framework is coherence preservation. Mathematical structures, in this view, simply should not break coherence at their lowest, most fundamental levels. Defining 0, 0, 0 ensures this continuity. It allows for stable, consistent emergence of more complex structures from the simplest starting point. It maintains the harmony, the consistency, right at the origin.
That makes perfect sense for the core axiom itself. But what about the other troublemakers, like dividing 0 by 0?
Right. Take 0, 0, traditionally labeled indeterminate. In coherence mathematics, this doesn't lead to an undefined void or an error message. Instead, it results in what the paper calls a coherence equilibrium state.
Equilibrium, like a balance point.
Exactly. Think of it like a perfectly balanced scale. Instead of just breaking or giving no answer, a new coherence attractor emerges. The system reconfigures itself to maintain that fundamental balance, that coherence, stabilizing at an invariant quantity. It finds a new stable state.
Okay, interesting. What about infinity minus infinity? Another classic headache.
Indeed. Infinity, infinity. Here, infinities aren't treated as just boundless quantities that mysteriously cancel out. They're treated as coherence gradients.
Gradients, like slopes.
Kind of. Think of them as representing directions or potentials of coherence flow. Their interactions are then shown to stabilize at coherence invariance. It's not about two infinite things arbitrarily vanishing. It's about their underlying coherence gradients interacting to find a stable state, a new point of equilibrium in the overall system. Coherence finds a way to balance even seemingly infinite tensions.
Wow. And the last one you mentioned, 0 to the power of infinity?
Zero infinity, another undefined exponential form. Again, if coherence is fundamentally conserved, this form doesn't just explode or vanish into ambiguity. It converges to a specific limit, one governed by what the paper calls coherence selection. The system selects the outcome that preserves overall coherence, ensuring stability even under these extreme conditions.
So, in essence, mathematical coherence is presented as a fundamental conserved quantity, like energy or momentum in physics, maybe, ensuring stability and self-consistency even at the very limits, where things normally seem to break down.
That's a great analogy. It implies that the universe, and the mathematics describing it, is fundamentally robust and self-consistent. It's designed for continuous emergence, even in situations where our current, perhaps more fragmented frameworks perceive a breakdown or an undefined state.
That's a truly different perspective than just declaring something undefined and moving on. It suggests an underlying, well, coherence to reality itself.
Absolutely. It implies the universe isn't built on shaky foundations with gaps and undefined zones. It's built on a principle that ensures continuous, stable, harmonious emergence from the ground up. It's a profound shift. Now, this foundational axiom, 0, 0, yield 1, isn't just sitting there in abstract mathematics. It's the launch pad. It's the starting point for a truly expansive and all-encompassing vision called the Unified Coherence Theory of Everything, or UCTE.
Theory of everything. Okay, that's a phrase that certainly captures attention. It's a bold claim. So beyond abstract math, what are the main domains UCTE extends its principles across? Where does this coherence lens take us?
It's incredibly ambitious. I mean, really ambitious. It claims to extend its principles across virtually all known scientific and philosophical disciplines we're talking about. Mathematics, obviously stabilizing structures, resolving those undefined cases we just discussed, that's the foundation.
Right.
But then it plunges straight into quantum mechanics, redefining the observer function not as some mysterious collapser of wave functions, but as a dynamic coherence modulator.
A modulator, like tuning a radio.
Sort of, yeah.
Yeah.
Actively participating in maintaining the coherence. It extends to field theories, explaining fundamental gauge symmetries, the rules governing forces as emerging from an underlying asymmetrical hypersymmetry, all linked by processes of coherence reduction.
Okay, hypersymmetry. We'll need to unpack that.
We will. It even ventures deep into cosmology, proposing that the elusive dark energy and dark matter making up most of our universe's budget actually arise from coherence-selected vacuum fluctuations and potentially neutrino condensates.
Wow, explanations for dark matter and energy from 001. That's quite a leap.
It is. And finally, it has significant implications for AI and computation, suggesting entirely new architectures based on coherence conservation that could lead to more robust, stable, and perhaps truly intelligent systems.
This is clearly a whole new way of thinking about reality, and it comes with its own language, its own lexicon. So before we dive deeper into the framework itself, let's clarify some of these core concepts. This is your essential guide to coherence physics.
Absolutely. Understanding these specific terms is really crucial for grasping the theory's true scope and its, well, internal logic. First up, coherence selection. This is the fundamental principle. The idea that physical and mathematical structures emerge because coherence is conserved and stabilized across transformations.
So things happen the way they do because it's the most coherent way for them to happen.
Essentially, yes. Think of it like a river carving a canyon. It doesn't just randomly meander. It finds the most stable, coherent path through the landscape over time. The universe, in this view, always selects the most coherent outcome available to it. It's not random chance-driving emergence. It's this drive towards coherence.
So it's not randomness, but a guided emergence towards stability. Okay. What about the mathematics itself?
That brings us to invariant ondilectic mathematics. This is the specific mathematical framework built upon the 001 axiom, designed explicitly to ensure coherence is preserved as a fundamental invariant throughout all mathematical operations and structures. It's the rulebook for coherence.
Got it. And the universal field tensor, UFT.
Right, the universal field tensor, UFT. This is a proposed field formulation where all physical forces and dimensions, gravity, electromagnetism, everything, emerge from these coherence reduction processes. Think of it like different facets emerging as you cut a single perfect crystal. They all come from the same underlying structure.
And how does this connect to something as fundamental and usually separate as gravity?
That's where hypergravity comes in. It's described not just as another force, but as a fundamental coherence field that unifies gravity intrinsically with quantum fields and all the gauge interactions. Instead of gravity being the odd one out, it's woven in through this shared principle of coherence.
Interesting. And gauge symmetry as asymmetrical hypersymmetry, that sounds complex.
It is complex, but the core idea is elegant. Gauge symmetry as asymmetrical hypersymmetry proposes that the fundamental force interactions we see electromagnetism, the strong and weak nuclear forces, aren't fundamentally separate. They emerge from a singular overarching hypersymmetry that then undergoes specific coherence reductions. It breaks down asymmetrically into the specific symmetries governing the forces we observe.
So a deeper, unified symmetry breaks to give us the diversity of forces we see.
Precisely. A symmetry breaking driven by coherence selection.
Okay. And for AI, you mentioned new directions.
Indeed. For AI, the paper introduces coherence neural networks, CNNs, not convolutional, but coherence neural networks. These are proposed AI architectures designed specifically to retain coherence memory. The idea is to prevent the kind of data fragmentation and catastrophic forgetting that often plagues current AI systems when they learn new things.
So AI that remembers coherently.
That's the goal. And quantum AI via coherence selection is an even more advanced AI paradigm proposed for quantum computers. Here, coherence maximization itself governs decision-making and learning, aiming for intrinsically stable, robust, and potentially far more powerful quantum intelligence than current approaches might allow.
So these are quantum systems that inherently resist errors because they're fundamentally based on this coherence principle, not just fighting against decoherence.
Exactly. In the realm of quantum physics itself, coherence eigenvalues are proposed as new measurable properties for predicting quantum behaviors, offering a different way to characterize and understand quantum states based on their coherence. And coherence-preserving quantum circuits are the physical architectures that would utilize this principle. Quantum computing architectures, using coherence conservation to actively eliminate decoherence errors, which is, as you know, the massive hurdle holding back scalable quantum computing right now.
That could be an absolute game changer if it pans out.
Huge.
And in the grandest scales of the universe, cosmology.
In cosmology, there's coherence-based cosmology. This is a framework where dark matter, dark energy, and the overall evolution of the cosmos are dictated by coherence dynamics, offering an alternative to models relying solely on entropy and initial random fluctuations.
A universe striving for coherence, not just winding down.
In a sense, yes. The observer function as a coherence modulator reframes the observer's role in quantum mechanics. Instead of collapsing wave functions, the observer modulates coherence, becoming an integral active participant in maintaining or selecting coherent states. It makes the observer part of the coherent system.
Less passive.
Much less passive. Neutrino condensate dark matter is a specific testable hypothesis arising from this. The dark matter is composed of coherence-selected neutrino states, forming vast, stable condensates. It offers a concrete candidate particle based on the theory's principles.
Okay, a specific prediction.
Yes. And finally, the coherent symmetry group, CSG, is a proposed new algebraic structure based entirely on coherence transformations. Think of it like the well-known Lie groups that describe continuous symmetries in physics, but completely re-envisioned through this fundamental lens of coherence preservation and selection.
That is a lot of incredibly dense and new ideas. But what stands out to me is just how ambitious this is. To redefine the entire universe, from math to AI to cosmology, through this single lens of coherence, all stemming from 001. It really is an expansive new language to describe reality, isn't it?
It truly is. It's a deliberate, systematic effort to move beyond piecemeal solutions and propose a genuinely unified and intrinsically coherent understanding of everything. It's a framework that suggests the universe isn't just orderly by chance, but fundamentally deeply harmonious at its core.
Okay, so to truly grasp how everything emerges from this concept of coherence, from those abstract universal principles down to the individual particles we observe, the paper proposes a layered framework for mathematical physics. You called it a cosmic blueprint earlier. Why this particular structure? Why layers?
It's all about bridging scales, really, and about reconciling different aspects of reality that often feel disconnected in traditional approaches. Think about abstract mathematics versus concrete physical application. They often seem worlds apart.
Right, pure math versus applied physics.
Exactly. This layered framework aims to explicitly show how those invariant mathematical principles, the really abstract stuff, directly govern physical systems. It's also meticulously designed to capture emergence. How do complex things like atoms or galaxies or even consciousness arise naturally from these fundamental invariants? The layers provide the steps.
Like levels in a building.
Kind of, and crucially, it links universality and specificity. It demonstrates how very general, unifying principles, the rules on the top floor, may be transitioned systematically into the particular systems we observe down here on the ground floor, like specific fields, waves, and particles.
So it's like a multi-story building where each floor reveals a new level of complexity and manifestation, but they're all connected by the same foundational structure. It's a definite step-down process from the most unified and abstract down to the specific and concrete.
Exactly, a cascade of coherence, maybe. And the first most foundational layer, the absolute bedrock, the penthouse suite, if you like, is Omnilectic mathematics. This is the absolute foundation, ground zero. It encapsulates invariant, unified principles existing in a state of perfect hypersymmetry and absolute coherence. The paper describes it as existing in a universal framework in hyperspace prior to what it calls the big emergence, before our familiar universe took shape.
Prior to the Big Bang, even.
The implication is yes, or at least prior to the differentiation we see. Imagine it as the universe's primordial, perfectly balanced blueprint. It encodes all possible mathematical structures, but in an undifferentiated, pure potential state. It's the ultimate source code, completely uncompiled.
Undifferentiated state sounds almost like a cosmic hum before the universe really started playing its tune. What are its key characteristics?
Its key properties are quite profound. There's universality. It encodes all potential mathematical structures in this unified, undifferentiated soup. Then there's invariance. These are the immutable principles, the fundamental conservation laws, the universal symmetry operators that never change, the bedrock rules, and finally, absolute coherence. Perfect, unblemished alignment of all potential components. There are simply no internal contradictions, no discord, no static at this foundational level, just pure, perfect harmony.
Can you give us some mathematical examples of what exists at this almost platonic level? What's in this omnilectic layer?
Certainly. We're talking about the fundamental symmetry groups that underpin physics, things like SUN, SON, and U1, crucial for quantum mechanics and particle physics. Also, the related Lie algebras like SU2, describing angular momentum. It encompasses the universal constants pi, E, the speed of light c, Planck's constant h, the gravitational constant g. But here they're seen not just as measured values, but as inherent invariant structural properties of this layer.
So they're not arbitrary numbers, they're part of the fabric.
Exactly.
Yeah.
It also includes abstract algebraic structures, like the field of complex numbers in its purest form, and fundamental conservation laws, as described by Noether's theorem, but again in their most abstract pre-manifestation essence.
And how does this incredibly abstract layer, this cosmic blueprint, connect to our physical reality? What's its so what for the universe we experience?
Physically, it's interpreted as reflecting the undifferentiated hypersymmetry of the very early universe, before any structure truly solidified. It serves as the ultimate source for all the symmetry-breaking processes that would later give rise to distinct forces, particles, and dimensions.
The origin point for complexity.
Precisely. Philosophically, it suggests a pre-emergent reality. It implies that mathematics, in its purest form, exists independently of the physical universe and even human cognition. It's the source of order, not just a description of it. It means that order, not chaos, is the ultimate default state of reality, even before anything emerges.
Okay, moving down a layer. From this absolute undifferentiated omnilectic state, how do these invariant principles start to, well, differentiate? How do they manifest as something a bit more dynamic, less static?
That's where holectic mathematics comes in. This is the layer where those omnilectic invariants begin their differentiation. They start to manifest as continuous field-like structures. The term holectic emphasizes holism, the interconnectedness, the idea that the whole is greater than the sum of its parts.
Hololectic, like holographic.
There's a resonance there, yes. If Omnilectic was the universe's perfectly still, undifferentiated blueprint, hololectic is where that blueprint begins to breathe and flow. It becomes a vast, continuous field. Imagine the ocean itself, not just individual drops or waves, but the vast interconnected body of water, where energy flows smoothly and every part is subtly connected to the whole. That's the essence of hololectic math.
So it's about continuous systems where everything is connected, flowing. What are the defining characteristics of this layer?
The key properties here are continuity, describing systems as smooth, unbroken structures like fields and manifolds. Holism, as we mentioned, which models entire systems, focusing on the interplay of components within a coherent framework, emphasizing the whole over the parts. Crucially, there's a strict preservation of coherence. The absolute coherence from the omnilectic layer isn't lost. It's fully retained and expressed through these continuous fields. And this is the first level of true manifestation, where those deep invariants start to differentiate into potentially observable mathematical and physical structures, but still in a smooth, continuous form. No particles yet, just fields.
Can you give us some examples of the mathematical tools and concepts at this hololectic level? What kind of math lives here?
Think of tensor fields. The prime example is the Riemann curvature tensor in general relativity, describing space-time curvature as a smooth, continuous field dictating gravitational effects. We also have differentiable manifolds, like the four-dimensional space-time manifold itself, providing the mathematical stage for continuous systems where calculus applies. Gauge fields are key, like the electromagnetic field AMU, governed by U1 symmetry, continuous fields encoding force interactions. Hilbert spaces, like L2-RR, used for quantum wave functions, representing the continuous state space of quantum systems before measurement. And differential operators, tools like the Laplacian, Dirac, or Klein-Gordon equations, which act on these fields to describe their continuous dynamics and evolution.
And how does this hololectic layer connect to our physical world? What's the profound implication here beyond the math?
This layer corresponds directly to the observable physical fields we know: electromagnetic fields, gravitational fields, and the quantum fields that underlie particle physics, representing particles as excitations of these continuous structures. What's also fascinating, philosophically, is that the paper suggests consciousness itself might be modeled as a field-like phenomenon emerging from hypersymmetry, utilizing these very hololectic mathematical tools like tensor networks and Hilbert spaces.
Consciousness as a field. Wow.
That's a provocative idea within the framework. Overall, this layer models the universe as an interconnected whole, a seamless fabric. It serves as the fluid conduit between that invariant abstraction of the omnilectic layer and the more dynamic relational systems we'll see next. The profound implication: reality isn't fundamentally composed of discrete bits, but of continuous interconnected fields, a grand flowing symphony rather than just isolated notes.
Okay, so from these continuous fields that embody the whole system, we move down another layer to relational mathematics. This seems to focus on the individual parts within those fields and how they interact. It's about the dance, the connections, the waves within the ocean. What characterizes this layer?
That's a perfect analogy. Relational mathematics zooms in on the interactions, the transformations, the connections between entities or regions within those hololectic fields. It often manifests through oscillatory or wave-like behaviors. It's about how parts within the system relate to each other dynamically, creating patterns and resonances. It's not just the whole system in isolation, but how the elements within that system dance together.
So less about the ocean, more about the specific waves and currents and how they influence each other.
Exactly. And its refined properties reflect that focus. We have localized relationality, emphasizing specific relationships between components, mappings, geometrical connections, interactions, rather than just isolated entities or the field as a whole. Then there's abstract periodicity, describing periodic, cyclical, or resonant behaviors in a generalized mathematical sense. This underpins physical waves, but it's a broader concept of cyclical relationships. Interconnectivity is still key. Coherence is maintained across systems by describing how dynamics preserve or propagate these connections. And finally, symmetry preservation and reduction. It retains vestiges, echoes of the higher hololectic symmetries, but they're expressed now as specific relational transformations and interactions. Some symmetry might be broken, leading to more specific relationships.
What are some of the mathematical definitions and examples we see here? What tools capture these relationships?
This is where we find incredibly powerful tools like Fourier analysis. It beautifully decomposes complex functions or signals into simpler sinusoidal components, revealing those underlying harmonic relationships, pure relational math. We see wave equations themselves, the partial differential equations describing propagation and periodic behaviors like light waves, sound waves, or quantum wave packets. Graph theory is crucial here too, as the mathematical study of relationships between vertices and edges, perfect for modeling complex networks, interactions, connections.
Like neural networks, maybe.
Absolutely, or any system defined by its connections. Topology and homotopy also fit, describing properties and transformations that preserve relational connectivity, like the fundamental group pi1m, which captures loops in a space. And of course, quantum wave functions as solutions to the Schrödinger equation are prime examples, describing probability, amplitudes, and phenomena like superposition and entanglement, which are fundamentally about relationships between states or particles. Even Lagrangian mechanics, deriving dynamics relationally by minimizing the action, the difference between kinetic and potential energy, fits perfectly into this relational layer.
How does this manifest in the physical world, and what's its profound implication? Where do we see this relational layer in action?
This layer underpins all of wave mechanics, quantum interactions, and relational geometry. It describes how those continuous electromagnetic fields from the hololectic layer give rise to observable, propagating waves of light, or how the Riemann curvature tensor, hololectic, defines the specific relational connections within space-time, relational, that dictate how objects move and interact gravitationally. Philosophically, it highlights that reality, at this level, is fundamentally defined by relationships and interactions. Resonance emerges as a key principle. It shows how localized dynamics and specific interactions arise naturally within broader continuous frameworks, emphasizing that nothing exists in isolation. Everything is interconnected through these coherent dynamic relationships.
And finally, we move from these intricate dancing relationships, the most concrete, discrete forms we observe in our everyday experience. That brings us down to the ground floor. Derived mathematics.
This is the layer where those localized relational dynamics get, well, crystallized, you could say. They're quantized, symbolized, or discretized into finite measurable forms. It's where the continuous flow resolves into discrete, countable entities. It underpins the observable, tangible phenomena we encounter daily. Imagine those individual drops of water finally splashing, or specific crests of waves that you can point to and count within the ocean. That's derived mathematics in action.
What are its key properties, and how does coherence still play a role here, even when things become discrete?
The primary properties are, first, quantization. This is the reduction of those continuous or relational dynamics into discrete, countable entities. Think particles, integers, specific energy levels, eigenvalues. Then there's symbolism and representation, encoding these discrete systems in abstract, symbolic forms that we can manipulate for calculation and computation, like algebraic equations, matrices, or numbers themselves. Even with this discreteness, there's a vital property: discrete coherence. The underlying coherence inherited from the previous layers is still retained, ensuring consistency and preventing the discrete parts from becoming completely fragmented or contradictory. It's like the pixels on a screen still forming a coherent image. And finally, practical utility is a major feature. This layer forms the basis for all our computation, measurement, symbolic reasoning, and applied science and engineering.
Can you give us some mathematical definitions and examples here? What does derived math look like?
Absolutely. This layer includes familiar territory: number theory and modular arithmetic, the study of integers and their relationships. We see eigenvalues and eigenvectors, those discrete solutions to linear transformations that pop up everywhere, like the distinct energy levels in quantum mechanics. Combinatorics, the study of discrete arrangements, permutations, combinations, belongs here. Foundational algebraic structures like groups, rings, and fields, which often encode discrete symmetries, like ZPZ in modular arithmetic. Finite graphs and matrices providing discrete representations of relational structures, like adjacency matrices for networks. The discrete Fourier transform, DFT, which converts sampled discrete data into discrete frequency components essential for digital signal processing. And even cellular automata, those fascinating discrete grids evolving based on simple local rules, like Conway's game of life, are perfect examples of derived systems emerging from underlying principles.
And how does this connect to physics, and what's its final profound implication? Where do we encounter this physically?
Physically, this layer corresponds directly to the world of particle physics, electrons, photons, quarks, viewed as discrete entities. It includes lattice systems used in condensed matter physics to model materials with discrete atomic structures, like the Ising model. And of course, it encompasses all digital representations in computing. Philosophically, it reflects the culmination of that cascade of symmetry, reduction, and coherent selection. Continuous coherence finally resolves into discrete, measurable units, It aligns perfectly with the quantized nature of physical measurements. We always measure discrete values and the crucial role of symbolic abstraction and computation in our human understanding and manipulation of reality. The profound implication. Even the seemingly discrete and individual particles or data points that make up our world are not truly isolated fundamental bits, but are emergent manifestations of deeper, continuous, coherent relationships inherited from the layers above. They carry the echo of the whole.
This is clearly a monumental undertaking, constructing an entire universe, from math to physics, from first principles of coherence. Why is such a comprehensive ontology valuable? What does it do for us, for mathematics and physics, beyond just being an interesting intellectual structure?
It does several critical things that current frameworks, often working in silos, really struggle with. First, as we've seen, it bridges the abstract and the applied with unprecedented clarity. It explicitly shows the pathway, the mechanism, connecting highly abstract mathematical principles, like those in hypersymmetry, directly to tangible real-world phenomena, especially in complex areas like quantum mechanics, general relativity, and cosmology, where those connections can feel murky.
It maps the territory.
Exactly.
Right.
Second, it provides a powerful generative framework. Instead of just describing existing phenomena after the fact, it offers a plausible mechanism for understanding how physical theories and structures actually emerge from mathematical ones. Remember the symmetry reduction in Omnilectic math leading to gauge fields and wave equations? That's a generative process.
So it predicts why the laws are the way they are, not just what they are.
That's the ambition, yes. Third, it dramatically expands the scope of mathematical ontology itself. It unites abstract math, relational structures, and the emergent nature of physical reality under one roof. This aligns beautifully with modern paradigms like relational quantum mechanics, which also emphasize relationships. And finally, look, this isn't just philosophy for its own sake. It has immense potential for practical impact, guiding the development of new theories, suggesting new computational approaches, potentially leading to new technologies based on coherence principles. That's incredibly exciting for the future of science.
So it's not just a new way to describe what we already know, but a potential engine for discovering what's next.
Right.
How does this layered framework compare to the traditional philosophical views on mathematical ontology? You mentioned Platonism math is discovered and formalism math is invented. Is this framework trying to replace them? Pick a side.
It's actually more ambitious than simply replacing them or picking a side. The framework aims to transcend these traditional views by integrating and unifying multiple perspectives within its layered structure. It finds value in each.
How so?
For instance, that absolute hypersymmetric omnilectic layer, where timeless mathematical truths exist independently, strongly resonates with Platonism. The relational layer, with its intense focus on connections, structures, and interactions, definitely echoes structuralism. Then the derived layer, involving human-constructed abstractions, symbolic systems, and computation, touches on aspects of nominalism and formalism.
So it finds space for all these different views at different levels.
Exactly. Even intuitionism and constructivism, which emphasize the constructive process of mathematics, are reflected in the framework's core idea of dynamic emergence through symmetry reduction. And both empiricism, connecting to observable physics, and universalism, describing universal laws, are woven throughout. It's trying to build a bigger, more inclusive tent, showing how these seemingly competing views might all capture a part of the deeper truth.
That's a very synthesizing approach. What are the key innovations, then, that make it stand out as a truly unique ontological framework, beyond just combining old ideas?
Several key things make it unique. First, obviously, the integrated hierarchical structure itself. It avoids the fragmentation of many traditional ontologies and explicitly shows how everything fits together layer by layer. Second, the profound focus on dynamic emergence through symmetry reduction and coherence selection. This introduces a process-based, almost evolutionary view of mathematics and physics that's often missing in more static ontologies. Third, it posits a unified relational absolute duality. It brilliantly resolves apparent contradictions by showing how absolute invariant principles, omnilectic, naturally manifest through relational dynamics, hololectic relational. And perhaps most profoundly, it fundamentally situates mathematics within a hypersymmetric context that's tied directly to this unified coherence theory of everything, HHC or TOE, another acronym used in the paper. It gives mathematics a physical, generative role in the cosmos, not just a descriptive one.
One of the biggest challenges, maybe the biggest, in foundational mathematics, and one that often gives mathematicians and philosophers genuine headaches, is Gödel's incompleteness theorems. These theorems famously suggest that any sufficiently expressive formal system, like arithmetic, can't prove all its own truths without risking inconsistency. It seems to put a fundamental limit on mathematical self-knowledge. How does this framework, claiming to be a foundation for everything, approach that formidable challenge? Does it claim to overcome Gödel?
That's a brilliant question, and it's a very, very clever move the paper makes. It doesn't claim to violate Gödel's theorems within their domain. Instead, it essentially sidesteps those potential pitfalls by externalizing the ultimate axiomatic basis.
Externalizing how?
Instead of relying solely on mathematics to prove its own ontology, which is the self-referential loop where Gödel's theorems bited, grounds mathematical truths in the principle of hypersymmetry reduction. This hypersymmetry, the state of the omnilectic layer, is presented as existing outside or prior to the conventional formal system of mathematics as we usually practice it.
So hypersymmetry is like a metasystem, a pre-mathematical foundation.
You can think of it that way, yes. It acts as a metasystem, or a cosmic precondition from which mathematics emerges. By rooting the ultimate justification there, it avoids direct reliance on the kind of self-contained proof structures that Gödel showed have inherent limitations. It's like trying to pull yourself up by your own bootstraps. Gödel showed that's impossible within a closed formal system. But this theory essentially gives mathematics a set of meta-bootstraps anchored in hypersymmetry.
So it's almost like it's saying the ultimate truth or consistency of mathematics isn't proven within math itself, but is guaranteed by this deeper pre-emergent principle of coherence and hypersymmetry from which math arises. That's quite a twist.
Exactly. Furthermore, by modeling mathematics as a dynamic process, a process of symmetry, reduction, and coherence generation, it embraces dynamic emergence. This avoids treating mathematics as a purely static, fixed, self-contained system, which is the primary context where Gödel's limitations most strongly apply. Gödel applies to static snapshots. This theory describes a movie. And finally, the proof within this framework relies heavily on relational principles and transformations, how coherence flows and structures emerge through the layers, rather than on absolute, potentially self-referential statements about truth within a single layer. This process-based relational methodology allows it to construct its ontology without running headfirst into the same kind of self-reference paradoxes that Gödel highlighted. It's a very elegant conceptual maneuver around a very thorny foundational problem.
And the paper uses category theory to formalize all of this, to build that rigorous mathematical structure connecting the layers. Category theory can be quite abstract. What makes it the right tool for such an ambitious unification project?
Category theory is almost perfectly suited for this, precisely because of its abstract nature and its core focus. It fundamentally emphasizes relationships, the mappings or morphisms between mathematical structures, often more than the objects themselves.
Which fits perfectly with the relational layers.
Exactly. It aligns beautifully with the framework's core focus on how coherence and structures transform, interact, and relate across different levels. Its universality is also key. Category theory provides a powerful unifying language that can describe vastly different mathematical disciplines, algebra, topology, logic, within a single conceptual framework. That's absolutely essential for a theory of everything that seeks to connect, well, everything.
A universal translator for math.
In a way, yes. Its inherent relational focus mirrors the view of holectic and relational mathematics emerging dynamically through processes of hypersymmetry reduction, and the ability to represent dynamic systems and transformations through its core concepts. Objects, morphisms, functors, natural transformations makes it the ideal language for rigorously describing the symmetry reductions and the transitions between the different layers of this entire HHHTR-TOE framework.
Okay, so if I'm picturing this correctly using the category theory lens, hypersymmetry, that omnilectic layer, is like the ultimate cosmic blueprint, an incredibly rich meta-category, maybe.
You could think of it that way, yes.
And category theory then gives us the precise rules, the mathematical machinery, the functors for how that blueprint unfolds, layer by layer, how symmetry reduces, how coherence flows, leading eventually to the math and physics we see.
That's a very good way to visualize it. The goal is to construct a formal proof outlining the absolute foundation. Hypersymmetry is perhaps a terminal object or a source category, then demonstrating symmetry reduction via specific functors. These are the structure-preserving mappings between categories. These functors would describe the emergence of relational mathematics, categories of fields, waves, graphs, and then further functors or constructions would derive tertiary mathematics, categories involving discrete structures, numbers, computation.
And consistency is key.
Absolutely. Throughout this entire construction, consistency would be ensured using tools like commutative diagrams in category theory. These diagrams are like mathematical blueprints that guarantee all the pieces fit together coherently. The different paths of transformation lead to the same result. It's a truly grand vision for formally unifying everything, from the most abstract principles down to the particles around us, using the powerful relational language of category theory. Now let's explore how this foundational axiom 001 and this elaborate layered framework translate into real-world applications and, crucially, unification across diverse physics domains. The core assertion here truly is that this entire framework provides the first genuinely unified foundation. It aims to seamlessly bring together mathematics and physics, quantum mechanics and relativity, and even information theory with coherent structures, all under one consistent governing principle: coherence generation and preservation.
Let's start with quantum mechanics, often seen as the most enigmatic, counterintuitive area of physics. How does applying this coherence lens redefine the fundamental aspects of QM? What are the implications? Does it make it less weird?
It certainly aims to make it less paradoxical, perhaps revealing a deeper coherence beneath the apparent weirdness. It's a pretty radical reinterpretation. First, consider the wave function, QSI. Instead of seeing it as an abstract, probabilistic wave function, that fuzzy cloud of possibilities, it's viewed fundamentally as a coherence-preserving structure. Essentially, the paper suggests Cx equals Cx, where C represents a coherence field or function.
So the wave function is coherence.
In essence, yes. It embodies the coherence of the quantum state. This means that quantum collapse, the measurement problem, isn't some random, unpredictable event where possibilities vanish. It's reinterpreted as a specific selection effect driven by interactions with the environment, selecting a specific outcome from the underlying hypersymmetric coherence states that maintains maximum coherence in the overall system. This elegant redefinition, the paper argues, eliminates many long-standing collapse paradoxes, like Schrödinger's famous cat being neither alive nor dead until observed. The coherence was always definite, just distributed.
So observation isn't randomly creating reality from fuzziness, but revealing a pre-existing coherent selection.
Exactly. Observation interacts with and reveals the specific coherent state. Second, the fundamental equation of quantum mechanics, the Schrödinger equation, is actually derived within this framework starting from the 0001 axiom, with psi explicitly defined as a coherence-preserving function. This fundamentally implies that quantum states evolve deterministically based on coherence preservation, making them coherence-selected rather than fundamentally probabilistic at their core. The apparent randomness comes from our limited view of the total coherent system.
That's a huge shift from the standard interpretation. What about entanglement? Spooky action at a distance.
Entanglement gets a very natural explanation here. Instead of spooky action, it's understood as a direct consequence of coherence preservation across spatially separated systems. Entangled states are described as coherence-locked bivectors or similar structures. Their coherence is fundamentally linked, regardless of distance. This elegantly explains their instantaneous correlation without needing faster-than-light information transfer. The coherence was established initially and is maintained globally. Furthermore, this framework predicts the possibility of new types of multi-particle quantum states exhibiting unique, higher-order coherence properties beyond standard entanglement.
And the practical side, quantum computing.
Yes, for coherence-based quantum computing, CBQC, the theory proposes building coherence-preserving qubits. These wouldn't just rely on fragile superpositions susceptible to environmental noise, decoherence. Instead, they would operate through mechanisms like resonance stabilization, actively maintaining their coherent state based on the underlying principles. The claim is this could lead to inherently error-free quantum computation, revolutionizing the field by directly sidestepping the massive challenge of decoherence that currently limits practical quantum computers.
That would be truly transformative, removing the biggest roadblock. Now, what about the other pillar of modern physics? Space-time and gravity, the realm of general relativity. How does coherence impact our understanding of the cosmos's large-scale structure?
Here, too, coherence becomes the central organizing principle, offering a potentially unifying perspective with quantum mechanics. Space-time itself is redefined as a coherence gradient. It's not viewed as a fixed, independent geometric background, nor just a fabric warped by mass. Instead, it's seen as a dynamic coherence field. The space-time interval, ds2, the fundamental measure of distance in relativity, is proposed to be directly a function of coherence, perhaps something like ds2 equals c, dx2 plus data2 plus dd2, c2 dd2, where c is the coherence function. This means space-time isn't absolute, but emerges dynamically as a function of coherent stabilization across the universe, constantly seeking equilibrium.
So geometry itself is an emergent property of coherence.
Exactly. Which leads directly to gravity. When it comes to Einstein's field equations, the mathematical heart of general relativity describing gravity, gravity itself is treated fundamentally as a coherence function, or arising from coherence dynamics. Space-time curvature, therefore, becomes an emergent result of coherence flow and interaction across the framework's hyperdimensional layers, rather than an independent fundamental force. It's how coherence manifests on large scales.
Unifying gravity through coherence.
That's the goal. And familiar relativistic effects like time dilation and length contraction are seen not just as abstract geometric distortions due to velocity, but as coherence-induced transitions. They represent shifts in the underlying coherent state of a system relative to its environment, which manifest macroscopically as changes in the measured flow of time or length. It's a universe where geometry itself is a direct manifestation of underlying coherence principles.
Okay, quantum mechanics, relativity. Even information itself is redefined through this lens. That's quite a sweep across such diverse fundamental concepts.
Yes, the framework extends naturally to coherence-based information theory, CBIT. It proposes that information, its loss or preservation, is intrinsically linked to coherence, suggesting a deeper universal principle connecting physics and information.
So,
First, information itself is proposed as a coherence measure. Concepts like Shannon entropy, the standard measure of uncertainty or disorder in information theory, are reformulated directly in terms of coherence preservation, or lack thereof. So information isn't just bits, it represents a state of coherence within a system. Maximum information corresponds to maximum coherence.
interesting. And for quantum information?
Quantum information becomes coherent selection. Quantum computers, if built on CVQC principles, wouldn't just be manipulating abstract qubits and superpositions. They would fundamentally operate via coherence routing, actively guiding and transforming coherent states through the computation, selecting for the desired coherent output state. And perhaps most significantly, this approach offers a compelling potential resolution to the long-standing, deeply troubling black hole information paradox.
The paradox that information seems to be destroyed when it falls into a black hole, violating quantum mechanics.
Exactly. By defining information fundamentally as coherence preserved, perhaps expressed as I final, A initial, where C is a coherence preserving transformation, the theory suggests black holes don't actually destroy information. Instead, they act as complex coherence transformers, redistributing the infalling coherent states into the black hole's structure and eventual Hawking radiation in a highly scrambled but ultimately coherent way. Information is simply transformed and stored or re-emitted, never truly lost, perfectly aligning with the fundamental principle of coherence conservation.
That's a profound implication for one of physics' thorniest paradoxes. But this is all very theoretical. How would one even begin to test such a sweeping, all-encompassing theory? What computational models or experiments are proposed for validation? It's one thing to have a beautiful theory, another to connect it to empirical reality.
That's the crucial next step, of course. The paper doesn't just present the theory. It proposes specific, tangible computational tests and potential experimental avenues for validation. For quantum mechanics, quantum circuit simulations are proposed. These would involve computationally implementing coherence-based quantum gates, based on the CSG group perhaps, and comparing their predicted error rates, stability, and computational power against simulations of standard, decoherence-prone qubits under various noise models. Finding significantly enhanced stability could provide strong evidence for coherence-preserving qubits.
Comparing models directly.
Yes. For relativity coherence simulations would model phenomena like coherence-induced time dilation, or Lorentz transformations, based on the proposed space-time as coherence gradient principles. The goal would be to see if these models accurately predict observed relativistic effects, potentially even making novel predictions for extreme environments, like near black holes or in the very early universe that differ slightly from standard GR. And for the information paradox, black hole coherence retention simulations are suggested. These would involve complex modeling of black hole evaporation, Hawking radiation, under the assumption of strict coherence preservation versus classical or semi-classical models that allow information loss via entropy increase. Comparing the predicted information content and correlations in the outgoing radiation could offer a way to distinguish the theories. These are concrete avenues for exploring, testing, and potentially falsifying the theory's predictions using advanced computational physics.
So there are paths to verification, even if challenging. And you mentioned earlier this layered framework isn't just for QM and GR. It extends to other physical systems too, from thermodynamics to electromagnetism, showing that this coherence principle is truly universal across physics.
Absolutely. The framework is designed to be universal, And the paper explicitly lays out how its transition operators, remember, Tom Ho, analytic to hololectic, Thorel, hololectic to relational, Trelder, relational to derived, apply systematically across various physical fields. This demonstrates that precise step-down process, the cascade from omnilectic invariants to derived discrete phenomena, isn't just for the fundamental theories, but for everyday physics too.
Can you give an example? Maybe thermodynamics.
Sure. For thermodynamics, the framework shows a progression. You start with abstract, fundamental energy invariance and conservation laws, omnilectic. These manifest as continuous heat flow equations like Fourier's law governing temperature gradients in materials, allolectic. This leads to localized heat dynamics like convection currents or specific heat transfer mechanisms between interacting parts, relational. And finally, this resolves into discrete entropy states, like the Boltzmann entropy calculated from the microscopic arrangements of individual particles derived, where the overall disorder emerges from discrete microstates, but still reflects underlying energy conservation.
So even the messy world of heat and entropy, usually seen as the opposite of order, is ultimately rooted in and constrained by coherence principles.
Precisely. Or take condensed matter physics. It goes from the fundamental lattice symmetries of a crystal structure, omnilectic, to continuous elasticity tensors, describing how the material deforms as a whole under stress, hololectic. This then leads to phonon dispersion relations, which describe the allowed wave-like vibrations propagating through the lattice based on atomic interactions, relational. And finally, this manifests as quantized quasiparticles like phonons, discrete packets of vibrational energy, and magnons, discrete packets of magnetic excitation that behave like particles derived.
Fluid dynamics.
Same pattern. For fluid dynamics, it starts from the fundamental conservation laws of mass, momentum, and energy, omnilectic. These give rise to the continuous Navier-Stokes equations describing fluid flow fields, hololectic. These fields then exhibit complex relational dynamics like flow instabilities, turbulence onset, and vortices, relational. And finally, these can be analyzed in terms of discrete structures like turbulence spectra or quantized vortices in superfluids derived.
And electromagnetism, a classic field theory.
A perfect example. It starts with the fundamental U1 gauge symmetry underlying electromagnetism, omnilectic. This manifests as Maxwell's equations, describing the continuous electromagnetic fields, E and B fields, permeating space, omnilectic. These fields support propagating plane wave solutions, like light waves traveling, relational. And ultimately, interactions involving these fields reveal the existence of discrete photons, the quantized particles of light, derived.
It really does paint an incredibly consistent and unified picture, a universe where this underlying principle of coherence is fundamentally at play everywhere, cascading down through layers of increasing complexity, from the most abstract universal laws governing hypersymmetry to the specific discrete quantum particles that make up you and me. It's a deeply woven tapestry, isn't it?
It is. Whether it's the correct tapestry remains to be seen through testing, but it's certainly a remarkably comprehensive and internally consistent one.
We're an incredible journey into the ontology of mathematical physics. We've explored a vision that begins with the seemingly simple, perhaps even dismissed, axiom of 001. And from that single point, this framework constructs an entire layered universe where coherence isn't just a desirable property, it's proposed as the fundamental generative force behind all mathematical structures and all physical reality.
It's been quite a ride through a truly ambitious theory, hasn't it? We've seen how this framework takes aim at traditional views, challenges long-held assumptions about paradoxes in math and physics, and offers potentially elegant solutions. And it uses this powerful, highly abstract, but fundamentally relational language of category theory to describe the systematic emergence of everything, starting from universal invariance and hypersymmetry, cascading down through continuous fields and relational dynamics, all the way to the discrete particles and phenomena we observe in our labs. It's a bold synthesis, a grand attempt at unification that really demands we look at the very fabric of existence through a completely new lens, one where stability, consistency, and a profound inherent harmony, rather than randomness or fragmentation, are the fundamental drivers of reality.
It leaves us with so much to think about. Here's a final provocative thought for you, our listeners, to take away from this deep dive. If coherence is truly the fundamental driver of reality, as this theory proposes, and if our own minds, our consciousness, are capable of engaging with and even constructing derived mathematics from these deeper, more coherent layers, What new domains might we unlock? Could we develop intelligent systems based on coherence principles? Could we even explore something like hyperdimensional resonance engineering? Could understanding these principles allow us to consciously align with and perhaps even leverage the universe's inherent coherence in ways we can only just begin to imagine, maybe even influencing the very fabric of our reality?
And it raises an even more fundamental question, perhaps. If mathematics is truly self-manifesting through this universal process of coherence, how does our human cognition fit in? Our unique capacity for abstraction, for creativity, for discovering or inventing mathematical truths, are we merely reflecting this universal process? Or does our consciousness, perhaps modeled as a hololectic field itself within this theory, actively participate in the universe's ongoing self-cohering manifestation? Are we discovering something purely external, or are our minds, in some profound way, part of the symphony? What stands out to you from this deep dive into the ontology of mathematical physics? What resonates?